Today we're going to take a look at Chapter 7, which is tolerancing. Key points for tolerancing, okay, is if a feature size is toleranced, it is allowed to vary within a range of values or limits. Tolerancing enables an engineer to design interchangeable or replacement parts. Tolerancing is dimensioning for interchangeability. What is interchangeability? An interchangeable part is simply a mass-produced part, like a replacement part. How a feature is integrated. How is a feature on an interchangeable part dimensioned? The feature is not dimensioned using a single value, but a range of values. Here, for example, we have 1 inch. We could specify that can go from 1.005 down to 0.994. That is the range of values that dimension could be. Tolerance is the amount of size variation permitted. You can choose a tolerance that specifies a large or a small variation. Okay, for example, again, from 0.994 to 1.005, that gives us 11 thousandths, 0.011, 11 thousandths of an inch tolerance. Why do we want a part size to be controlled by two limits? It's necessary because it is impossible to manufacture a part without some kind of variation. The closer that variation is, the more expensive the part is going to be. Okay, the limits are a form of quality control. Choosing a tolerance for your design, specify a tolerance with whatever degree of accuracy that is required for design to work properly. If you have two parts that are going to fit together, okay, you might need a closer tolerance than if you have a part that just sits on top of another part and is not limited at all. Choose a tolerance that is not unnecessarily accurate or excessively inaccurate. Excuse me, I can't speak today. Okay, again, the more accurate we get, the more expensive it's going to be. Choosing the correct route for a particular application depends on the design intent, how it's going to be used, the cost, how it's manufactured, and experience. Tolerancing standards. We need standards to make it possible to manufacture parts at different times and in different places that will still assemble properly. Okay, take example, an automobile engine, okay, or parts to an automobile. They're not all made at one place at one time, but they're tolerant so that no matter where that part is made, it will fit into another part. Establish dimensional limits for parts that are to be interchangeable. The two most common standard agencies are the American National Standard Institute, ANSI, which is also controls the ASME, American Society for Mechanical Engineering, and the International Standards Organization, the ISO. Okay, we have different types of tolerances. We have limit dimensions, plus or minus tolerances, and page or block tolerances. Limits are the maximum and minimum size that a part can obtain and still pass inspection. For example, diameter shaft might be specified as, again, 1.001 down to 0.999 or 0.999 to 1.001. When we create these, if we stack them like this, the bigger number goes on top. If we put them across here, the smaller number goes first. Okay. Again, the high limit is placed above the low limit. When both limits are placed on one line, the low limit precedes the high limit. Plus or minus tolerances. Plus or minus tolerances gives a basic size and a variation that can occur around that basic size. So here we have 10 plus 0.1 minus 0.2. A page or block tolerance is a note that applies to all dimensions not covered by some other tolerancing. Okay, a common way of doing it is we can do the number of decimal places, and that will determine what the tolerance would be. Here also we're specifying that we're using the standards ASME Y 14.5 and then whatever version it is. Okay, we're going to take a look at how we can create this drawing. We have some tolerances here. For example, okay, we have a tapped 1224 UNC that is 0.63 deep. Okay, that is a countersink. Okay, it's 0.38 plus 4 minus nothing, and it is a 90-degree countersink. Here we have a dimension from the edge of the part to the center of this countersink, and that is 0.5 plus or minus 2. We have a dimension between those holes, which is 1.626 and 0.1625. Also have an overall dimension 2.625 plus or minus 1. We're going to take a look at drawing this drawing and specifying our tolerances, and then we're also going to look at some dimensioning shortcuts and different ways that we can do things that we haven't done before. So open up a new part. I am in inches and I went to the top view, right? So I'm going to go here, rectangle. I'm going to draw a rectangle. I'm going to start at the center point. Okay, and then I'm going to dimension. This dimension here is 2.625. This dimension here is 1.5. Okay, we have a cutout. Let's see, we'll do the cutout later. I'm going to finish the sketch, and then I'm going to extrude this up, and that is 0.625. I think the drawing calls out 0.63, so 0.625 is fine, and pick OK. So now I have this. Alright, I'm going to put the slot in it, and the slot is on this edge right here, so I'm going to go to start a new sketch, go to there. Okay, and I'm just going to take again and draw a rectangle, and I'm going to go from the center, and I'm going to go here, and then I'm going to dimension, and this dimension from here to here is 2.625 minus 0.94 divided by 2, which I'm hoping comes out to 0.75. And then I also have the depth here, which is from here to here, which is 0.25. Okay, so I have that one there, and I finished the sketch. I'm going to extrude that. Now I can just extrude this one piece. We don't have to worry about this bottom piece. It will fall off. I'm going to cut it all the way through. Okay, and there we have that. All right, now I'm going to start my holes. So I'm going to go to the hole. Okay, and I'm going to put it like right here. Okay, from this edge here is 0.5. Here it is in the center, which is 0.75. Okay, now here what I'm going to do, okay, if you notice on that drawing that it is a 1224 UNC and it is a countersink. So I'm going to go to screw threads, okay, and I'm going to go to right here. Okay, that's a tapped hole. Okay, then I want that to be a, what I say, 1224, so number 12. Okay, here's the 24. Okay, here are the different ones, but we have 1224. Okay, and we have a countersink. Okay, and it will automatically put the correct numbers there for us, I hope. Okay, now I wanted to change this to 90 degrees. Okay, countersinks can be a bunch of different angles. 82 is probably the most common, but I just wanted to show you changing that number. And then I want this thread to go all the way through 0.625. Okay. Now on the drawing though, I have a different dimension here. Okay, I have 0.38. So I can change this to 0.38. That changes the size a little bit. Okay, now if I look at that on the 3/8, I have a tolerance of +4 minus nothing. If I click this arrow right here, you'll see tolerance. Okay, and what I have is a deviation, a different plus and a different minus. So I've got plus 0.004, and I have minus nothing. Okay, and my precision I want to be 3 places, and I pick OK. Let's see, that is the only tolerance that I have here, and I pick OK. Now if I go to make another one and I put it here, okay, I can just put this number here 0.5, this number here 0.75, and all these will be the same. You see the little dot here, green dot, that means that there is a tolerance there, and I pick OK, and they're both in the right positions. Okay, we're also going to have a clearance hole with a counter bore up here for a 1/4 inch cap screw. So I'm going to pick hole, put it there. Now we'll center it this way. Here is 2.625 divided by 2. This edge here is 0.75. Okay, now we're going to say that we want a clearance hole and we want a counter bore. Okay, and this is a 1/4, and we want this for a socket head machine screw. Okay, notice if I use a hex head bolt, that counter bore is 0.75. If I go to a socket head cap screw, now it's going to go down to 438. Okay, all right, then the depth I have here 0.19. Okay, I want it to go through everything. You'll see that this is 0.266. It automatically, when I tell it's going to be a clearance hole for a 1/4 tap screw with a normal fit, that is what it's going to do. If I go here and make a loose fit, you'll see that that hole becomes bigger. Okay, so we want a normal fit. Okay, and I just pick OK, and now I have my part. Now of course now I go in here in the I properties and do the summary, and this is called tolerance, ANCE. Okay, it's drawn by me. Okay, and then again, if I had a stock number or anything like here, and let's make this, we make everything out of aluminum because aluminum is nice and easy to work with, and I'll pick aluminum and I'll pick OK. Alright, now I'm going to go to File, I'm going to do Save As because I need to save it before I make it, and I'm going to call this Tolerance 01. Okay, now I'm going to take and I'm going to open up our blank. Okay, so that is in inches, title block A size. Okay, we should probably be okay with the A size, but who knows, so we'll stay with that, and we should be good here. Now I'm going to take the base, and I want to show the holes, so I want the holes there, and I'm going to flip it around. Again, I didn't pay much attention to what it was, so now I've got it shown here. Excuse me. My scale 1 to 1 is probably pretty good. If I go to 2 to 1, okay, probably too big, half too small, and 1 to 1 is just right. So I'm going to pick OK. Alright, so now what I want to do is I'm going to make a section view. So I want this particular view. I'm going to go to the midpoint over here, right click, pick continue. Okay, this is AA, scales 1 to 1. It is a full section, and I'm going to put it like right here. Okay, and then I'm going to project from here a side view and pick create. Now you'll notice that the side view does not have any hidden lines in it, and I want to show the hidden lines, so I double click on it. Okay, right now it's getting the style from the base view, which is here. Okay, so I'm going to go style, and I'm going to change this to hidden lines and pick OK, and now I have my hidden lines. Okay, now what I want to do is I want to put my center lines. Now we looked at before, we can go over here, and if we're doing a hole we can put a center mark, then we can do the bisector. Well, we can also do automatic. So if I just take where I get the red line here, right click, I can go to automated center lines. Okay, wants to know what I want to apply it to. It's a hole, and I want it to be the objects round, and I pick OK, and there are my holes automatically, or my center lines put in automatically. Good stuff. Now I need the center lines for these holes. Again, when I get the red line, right click, automated center lines. Again, I want the circle, the hole features, but this time instead of in the normal view, I want it in the parallel to the axis. Okay, and I pick OK, and it puts those lines in automatically. Okay, again, right click on this one, automated center lines. I want the hole, I want this axis, and there it goes in there. Now I can take this one, just slide it out a little bit. Okay, and I might want to change my scale of those because I can't see them as center lines in here. So I go to Manage Style Editor. It's coming. Okay, and I go to my standard and pick standards, and here's my global scale, and I could change this to 0.5 maybe. Save and close. Now I got some nice center lines here. Okay, now what I'm going to do is I'm going to dimension the countersunk holes and the counter bored hole. I normally wouldn't do these first, I would do these probably last, but I just want to show it to you. I'm all excited about showing you. So I'm going to go into annotate, I'm going to go into holes and threads, and I'll pick on this one first, and I'll drag it down here, and you'll notice it's a 1224 UNC 2B. Here's the depth, here is the size of the, it tells us a countersink. Okay, and here is the size of the countersink. Okay, again we can pick on this guy, and there is our hole there. Okay, now what we don't have here, if you notice, we do not have our tolerances. Okay, we put some tolerances on these guys here. Okay, if I hit escape so I'm not in hole and thread anymore, double click on that dimension, okay, we'll get this, and there's all the stuff that's there. Okay, so I go to precision and tolerance, and now you hear right now it's using the global precision. Okay, I'm going to pick use part tolerance. Okay, and I'm going to pick OK, and I also want to go here back into it, and I want to take off use the global, and I want these to be 3 places. So I'm going to put the primary as 3 places. Okay, and that's for the center, and also here for a countersink I want that to be 3 places. Okay, and we also want our depth. I don't think we put a depth on there. Okay, but if we did, we could put a thread depth there, and I pick OK, and I pick OK, and now we have our tolerances here. Okay, all right, now what we're going to do is we're going to dimension these. Now we're going to look at a little bit different way of dimensioning than we did before. Okay, one thing I'm going to do is I'm going to take this here and I don't like it. It makes it too big. Now we could set that in the beginning, but you put so few in there. Just go here and change it. Okay, and I might want to move that, and I'll put it over here. Okay, now the first thing I want to do is I want to dimension from this edge to the center of this hole, and from the center to the center of that. Okay, to do that, I'm going to use a chain dimension. Okay, and with a chain dimension, remember, here's a picture of it. Okay, and it chains. So I go for a chain from here to here, and then from here to here. Okay, so I just pick the dimension I want, this one, center of that one, the center of that one. I right click and I pick continue. I drag it down here. I click, I right click, and I pick create. And automatically puts those dimensions for me. What it didn't put there is our tolerances. So I'll take this one first. Okay, and under precision and tolerance, okay, the dimension is 0.500 plus or minus 0.002. Okay, so that is a symmetric. It's the same upper and lower. The primary unit I want 3 places. The tolerance I want 3 places. I don't know why they don't have those match, because they should always match. Okay, and here I have a upper and lower of 2. I pick OK. Now I have my dimension point 500 plus or minus 2. Now here I'm going to have a, if I right click on it, double click on it, there we go. And this is going to be limits. Now I can have them stacked one on top of each other, or I can have them linear side by side. I'm going to make them stacked. And for the upper dimension I have 1.626, and for the bottom I have 1.625. And again, I want to change my decimal places on both of those to 3, and I pick OK, and now I have my limits there. I also have a dimension from here to the center, okay, without a tolerance. I also have a dimension from here to the center there, top or bottom, it doesn't matter. Okay, all right, now what I want to dimension is I want to dimension from here to here and to here and an overall. And what I'm going to do is I want this to use this as my baseline. Okay, so what I can do here is go to baseline and then pick the ones I wanted. I want to go from here to there, to there, to there. Okay, right click, continue, drag it down there, get the dotted lines, click on it, right click and pick create. Easy as that. Okay, the thing we need here is we need a tolerance here, which would be 2.625 plus or minus 0.001. Okay, I double click on that. I said I double click on that. Here it comes. And that I want to be symmetric. Okay, and I want 3 places. 3 places. Okay, and this is 0.001. And I pick OK. And there I have that dimension there. I could go into baseline again, and I could pick this line, and that line. Continue, drag them to where I want them, pick OK or create, and then I could do one more dimension, this line right here. Okay. All right, here what I want to do is there are 2 of those holes, so I want to put a 2 in here, so I can put my cursor to the beginning and put 2x space, pick OK. So now I have 2 of those. The last thing I can do, which is kind of neat, is I can make a isometric here, and I'm going to make an isometric of the section. So if I go to place view projected, click on this one and drag it to where it looks like good, looks good, right click create. I'll double click on that. I'll take this style off and I'll make it shaded so it doesn't go from here. Okay, I could also take this check mark off and change the scale if I wanted to, but it's okay if I use it from the base. Okay, I want to go to display options. I want to make sure that I have thread feature, and I pick OK. So now you see I have my threads here, I have my section lines, and there I have my drawing. Alright, creating tolerance is using the shaft and hole assembly where we have a shaft going into a hole. Okay, it's used to illustrate and concepts and definitions. Both the shaft and the hole are allowed to vary between a maximum and minimum diameter. Okay, so here we have a shaft. Here's the maximum diameter it's allowed. Here's the minimum diameter. Here is a hole. Okay, and the maximum diameter and the minimum diameter of the hole. And we talk about inches. We talk about limits. The limits are the maximum and minimum sizes that a part is allowed to be. The basic size is the size from which the limits are calculated. It's common for both the hole and the shaft and is usually the closest fraction. Okay, so it's usually the same number and it's to the closest fractional number. Tolerance is the total amount of specified dimension is permitted to vary. Okay, took a look at some more things. Alright, we're going to look at this. Here we have a shaft with its limits. Here we have a hole with its limits. Okay, when we talk about the shaft, the limits of course is from 47 to 51. The hole is from 49 to 50. The basic size will be the closest fractional number. Okay, in this case that would be 1/2 or 0.5. The tolerance would be from 47 to 51 and from 49 to 50. So 4 thousandths or 40,000, excuse me, and 10 thousandths. We talk about our tolerances. We have a maximum material condition, which is the MMC. The MMC is the size of the part when it consists of the most material. The least material condition, the LMC, is when the size of the part when it has the least amount of material. Okay, so again, it's different whether we're talking about the shaft or the hole. Okay, if we look at the shaft, the maximum material would be the largest the shaft is. The maximum material for the hole would be the smallest the hole is because now there's more material. Okay, so the MMC would be the largest shaft and the smallest hole, 0.51, 0.49. The LMC, the least material condition, is the smallest shaft, and then the least amount of material would be the largest hole. Okay, so from 47.47 to 0.5. The maximum clearance is the amount of space that can exist between the shaft and the hole. The maximum clearance is the LMC of the hole and the LMC of the shaft. The minimum clearance, or the allowance, is the minimum amount of space that can exist between the hole and the shaft. The minimum clearance is the maximum condition of the hole and the maximum material condition of the shaft. Okay, so if we look at something like this, the maximum clearance would be the smallest shaft and the largest hole. The minimum clearance would be the largest shaft, the largest shaft and the smallest hole. Okay, so we have the maximum clearance is the smallest shaft, the largest hole, or 0.03. The minimum clearance is the largest hole and the smallest hole and the largest shaft, okay, or negative 0.02. Okay, the negative clearance means that there is an interference. the shaft is bigger than the hole. When we talk about the shaft and hole, we have different type of fits. Okay, there are four major types of fits. There's a clearance fit, an interference fit, a transitional fit, and a line fit. Okay, a clearance fit, there's always a space. Okay, so always space between the shaft and the hole. The minimum clearance is greater than 0. An interference fit, there's never a space. The maximum clearance is less than or equal to 0. A transition fit, depending on the size of the shaft and hole, there could be a space or no space. So the maximum clearance is greater than 0, the minimum clearance is 0 or less than 0. A line fit, there is a space or a contact. So the maximum clearance is greater than 0, the minimum clearance is 0. Okay, look at types of fits. Everyday life lists some examples of clearance and interference fits. Clearance fits, we have things like a lock and a key, a door and a door frame, a coin and a coin slot. Interference, pin and a bicycle chain, a hinge pin, okay, wooden peg and hammer toy. These are interference fits. Okay, determine the basic size and type of the fit, okay, for the shaft and the hole. Okay, so we have a shaft that goes from 1.498 to 1.5 and a hole that goes from 1.503 to 1.505. Okay, what is the basic size and the type of fit? Okay, the basic size is the closest fraction. This would be 1.5. This is a clearance fit. Okay, the clearance in here is always greater than 0. If we take a look at the largest hole, which is 1.5, largest shaft, which is 1.5, and the smallest hole, which is 1.503, there's always a clearance. If we take the smallest shaft, 1.498, and the largest hole, of course, is going to be a clearance there too, so that's always going to be greater than 0. That is a clearance fit. Okay, if we have 0.751 to 0.755 for the shaft, 0.747 to 0.750 for the hole. Okay, the basic size is 3/4, 0.75. This is an interference fit. Okay, it is always less than or equal to 0. So if we take the largest shaft, which is 0.755, and the smallest hole is definitely that is less than 0. And if we take though the smallest shaft and the largest hole, that's still less than 0. So that is always going to be an interference fit. Okay, 0.373 to 0.378, 0.371 to 0.375. Okay, again, the closest fraction is 3/8, 0.375. That is a transition fit. The maximum clearance is greater than 0. The minimum clearance is less than 0. Okay, so the largest shaft is 0.378. The smallest hole is 0.371. Okay, that's less than 0. Okay, the largest hole shaft is 0.378. The smallest hole is 0.371. We have 0.247, 0.250. Okay, that is 0.25, 1/4 of an inch. That is a line fit. Okay, the minimum clearance can be 0, where we have our largest hole is 1/4, the smallest hole, our shaft is 1/4, smallest hole is 250, it equals 0. Okay, we have ANSI standards for limits and fits. The following fit types and classes are in accordance with the ANSI USAS B 4.1-1967 R 2004 standard. Okay, for clearance fit we have RC, which is a running or sliding clearance fit. These are intended to provide running performance with suitable lubrication. Okay, we'll look at the table in the back of your book for some of these fits. Okay, we do have 9 different fits where RC9 is the loosest and RC1 is the tightest fit. We have locational fits, LC, LT, LN. Locational fits are intended to determine only the location of mating parts. Locational fits are not for running machinery. It is for the location of mating parts. Some example parts of machines fixed to shaft using pins, bearing bushings, precise fits of machines and preparations, exchangeable wheels, bolts, retaining and distant ring, parts of machines fixed to shaft using pins, rivets or weld, and etc. An LC is a locational clearance fit, an LT is a locational transition fit, and LN is a locational interference fit. Then we have FN, which are force fits. Force fits provide a constant bore pressure throughout the range of sizes. Okay, again we have 5 different ones from FN1, which is the loosest, to FN5, which is the tightest. Okay, let's take a look at some examples. Given the basic size of 0.5 inches and a fit of an RC8, calculate the limits for both the hole and the shaft. Okay, in our book, it's the ANSI limits and fits table in Appendix A. Looks like that. Okay, so here we look for our size. Our size, our basic size is a 1/2 inch, 0.5. So 0.4 to 0.71, it would be this row here. Here's an RC5, RC6, RC7. Here's an RC8. Here are standard limits. For the hole, plus 2.8 and 0, and the shaft, minus 3.5 to minus 5.1. Okay, now when we look at these numbers, these are thousandths of an inch. So 2.8 would be 0.0028. Okay, 3.5 would be 0.035. Alright, so if we have 0.5 inches and a fit of RC8, okay, here is the hole, goes from plus 2.8, which is plus 0.0028, okay, plus 0, that's for the hole. For the shaft, negative 3.5, which is negative 0.0035 to minus 0.0051. Okay, these are the values that we add or subtract from the basic size to obtain the limits. Okay, so from the hole, okay, we take 0.5 minus 0 is 0.5000. Since we're going to 4 places, it must be 4 places in both places. And here we add 0.0028. So our hole can go from 0.5 to 0.5028. The shaft, we have minus 0.0035, which gives us 0.4965. And we subtract also 0.0051, which gives us 0.4949. We have a little bit different tolerancing methods. Okay, the definitions, limits, basic size, tolerance, MMC, and LMC are the same as in the inch tolerance we talked about. Okay, we'll look at some of the definitions. So here we have the shaft, the hole. Here's the shaft, here's the hole. The limits for the shaft are going to be 2.1 to 2.2, 1.8 to 2. The basic size will be the whole number. In this case it would be 2. The tolerance, subtract 2. Here the tolerance is 0.1. Here the tolerance is 0.2. The upper deviation. The upper deviation is the difference between the basic size and the maximum size, is the upper deviation. The lower deviation is the difference between the basic size and the minimum size of the part. The fundamental deviation is the closest deviation to the basic size. The fundamental deviation is the smaller of the upper deviation and the lower deviation. The letter in the fit specification represents the fundamental deviation right here. Okay, so if we take a look at this, the upper deviation for the shaft is 0.2. For the hole is 0. Difference between the nominals, so the basic dimension would be 2. So that's 0. The lower deviation would be 0.1, 2 minus 0.1, and 0.2, 2 minus 1.8. The fundamental deviation is going to be the lower, 0.1 and 0. Okay, here we have 2.2, 2.1, 2.0, 1.8. What type of fit would that be? That is an interference, because the shaft, the smallest this shaft can be is 2.1. The largest the hole can be is 2. There's always going to be an interference there. We have the International Tolerance Grade number. That is the number here. It's called the IT number. It's a set of tolerances that vary according to the basic size and provide some relative level of accuracy within a given grade. The number in the fit specification represents the IT number, 11. The smaller the number provides a smaller tolerance. We'll use those numbers when we look those up in our tables. The tolerance zone is the fundamental deviation in combination with the IT number defines the tolerance zone. The IT establishes the magnitude of the tolerance zone, or the amount that the dimension can vary. The fundamental deviation establishes a position of the tolerance zone with respect to the basic size. Following fit types are in accordance with ANSI B 4.2-1978 revision 2004 standard. Okay, so here are some basic numbers. An H11/C1 is a loose running fit. Then we have a free running, close running, sliding, locational clearance, locational transition, locational interference, a medium drive, and a force fit. Difference between the hole and the shaft basis, because you'll notice here we have a hole basis, here we have a shaft basis. We're going to talk about in a couple minutes. Tolerance designation. Fits are specified by using the fundamental deviation letter and the IT grade. When specifying the fit, the hole will be the uppercase letter, the shaft will be the lowercase letter. Okay, metric fit designations. Fill in the appropriate name. This here is the basic size. This here is the hole tolerance zone. This here is the shaft. Remember, we can tell the hole is the uppercase, the shaft is the lowercase. Okay, it's not because that one says H. Okay, looking at just the H, that is the fundamental deviation, and the 8 is the IT number. We have basic hole and basic shaft system. Metric limits and fits are divided into two different systems, the basic hole system and the basic shaft system. The difference is which one is going to be, either the hole or the shaft is going to be your basic dimension. For a basic hole system, it's used when you want the basic size to be attached to the hole. For example, if you want to tolerance a shaft based on a hole produced by a standard drill, reamer, broach, or another standard tool, then use the hole system. Shaft system is used when you want the basic size to be attached to the shaft dimension. For example, if you want to tolerance a hole based on the size of a purchased standard drill rod. Okay, identify the type of fit in the system used to determine the following shafts and hole pairs. Here we have the shaft deviation and the hole. So the type of fit here, okay, that's going to be a clearance. It is a hole system because the hole number is under hole. The hole number with a W is under the hole with an H. Okay, look at this one. That is a transition. Okay, that is a hole system. Okay, that's the hole number right there. Look at this one. That is an interference. Shaft is always bigger than the hole. This is a shaft system because there is the hole number. Okay, limits and fits. Find the limits, tolerance, fit, and type of system for a 30 diameter H11/C11 fit. Okay, looking at Appendix A. Here is Appendix A. Okay, find that. So we take a look at the H, that is the hole 11, C11. So here is the hole H11, C11. We want a diameter of 30. Okay, so here we go down to here, and here we have 30. Okay, the H11 C1 is a loose running fit. Okay, our hole can go from 30.130 or from 30.000 to 30.130. The shaft 29.760, 29.890. Notice the difference between this and the inch system is we don't have to do any adding, subtracting, multiplying, or nothing. Okay? Alright, so here again we have the limits of the tolerances for the shaft and the hole. Okay, it's 0.13. We take a look at here, the difference between here is 0.13. The hole is 0.13. Okay, same thing. The system, this is a hole system because it is a capital H, and because here is the hole number. The fit here is a clearance or a loose running fit. Okay, here we have the same size diameter, P786 fit. Okay, again we're looking at 30 max and we're looking at a P7H1. Here are our sizes for the hole, 29.986, 29.965. For the shaft, 30.000, 29.987. We already know what type of system this is. This is a shaft base because here is the hole number. Okay, the tolerance, okay, for the shaft is 0.013. Subtract those. And the hole is 0.021. The system is a shaft because the shaft is 30. The fit is a locational interference. And if we go back here and look, it tells us right here, it's a locational interference. Selecting tolerances. Tolerance will govern the method of manufacturing. When tolerances are reduced, the cost of the manufacturing rises rapidly. Okay, again, I mentioned a couple times, the tighter the tolerance, the more expensive it's going to be. Okay, so you want to specify as generous a tolerance as possible without interfering with the function of the part. Okay, be useless if it's cheap and didn't fit. So we have to kind of balance out the two. Choosing the appropriate tolerance depends on many factors: the length of engagement, the bearing load, the speed, lubrication, temperature, humidity, and material. Okay? Experience plays a significant role in this. Okay? That only comes with time. Okay, we have different IT grades depending on what we're doing. Okay, and this goes from the closest fit to the farthest. Okay, and here are IT grades. Okay, so lapping and honing is a 4 or a 5. Cylindrical ground, I can't say that. Cylindrical grinding is a 4, 5, 7. Die casting is an 11. Again, depending on what you need. If you're going to ream it, it's going to be between a 6 and a 10. Okay, and the smaller it is, the closer tolerance is going to be. Okay, tolerance accumulation. Okay, tolerance between two features in a part depends on the number of controlling dimensions. Okay, here we have 40 plus or minus 0.1, 20 plus or minus 0.1, 30 plus or minus 0.1, 20 plus or minus 0.1. The more dimensions we have, the more the tolerance can accumulate. The maximum variation between two features is equal to the sum of the tolerances placed on the controlling dimensions. Remember, even if the dimension does not have a stated tolerance, it has an implied tolerance. Okay, so we have a dimension, this entire length of this part. The tolerance of that length is going to be 0.1 plus 0.1 plus 0.1 plus 0.1. Okay, what is the tolerance accumulation for distance between surface A and B in the following three-dimensional drawing or three-dimensional methods? Here, what is the total accumulation between A here and here? Okay, it is 70, 30, 40, 50, 60, 70 plus or minus 0.3. Okay, if it were perfect, it would be at 70. The worst case would be 70.3. The minimum worst case would be 69.7. Okay, here, if we tolerance it this way, the total accumulation between A and B is 70 plus or minus 2. You see that it's a much closer tolerance. Now, it's a closer tolerance, but our tolerances are still 0.1. Okay, so it's not any more expensive to keep the whole disc to 40 plus or minus 0.1 than it is to hold it from here to here plus or minus 0.1 and from here to here plus or minus 0.1. Okay, but we don't have the accumulation. Okay, in this case, perfect would be 70. The worst case would be 70.2. So we don't have that much difference. If the accuracy of distance between surface A and B is important, which dimensioning method do you think we should use? It would be that one. Okay, so now what we've done is we just put a dimension here at 70 plus or minus 0.1. Still, our tolerance is plus or minus 0.1, but we made it from here to here. So we don't have that accumulation of tolerances. Tolerances from standard fit tables are listed in drawings. This is the way it is for a metric. Okay, the person reading the print has to have access to these standard fit tables to be able to figure these out. Okay, formatting metric tolerances, unilateral tolerances. Okay, a little different than the English where we can have plus nothing. We just put 10 there, minus point or 0.02. We normally put the leading zero in a metric drawing. Okay, or we can do it this way. If we have 0, we can leave the plus or minus off of it. Okay, bilateral. Okay, 10 plus 0.25 minus 0.10. Okay, notice that we need the same amount of decimal places on the upper and the lower, not this one. Limits, again, we need the same amount of decimal places. Okay, using base dimensions with tolerances, we have 4, 5 plus or minus 0.51. We don't put the number of decimal places in the basic dimension like we do in the inch method. Okay, that does not have to match. Okay, again on the inch tolerances. Okay, we don't want to put just a 0 here if we have plus nothing. We put plus, and we have to have the same amount of decimal places. Okay, in all numbers. Okay, this number, this tolerance, and this tolerance, no matter what they are, have to be the same number of decimal places. Same with the limits. We need the same number of decimal places. Using basic dimensions, again, we can put this here, but I don't like the leading 0. Okay, we don't have 2.0. Even these are zeros, they have to be the same amount of decimal places. Angles, okay, if it's a point, we need a point here. Okay, that takes care of that chapter on tolerances. Again, look in Canvas to see what your assignment for this particular chapter is.